computer. Hopefully you noticed on Zoom, or not Zoom, sorry, Slack right after class last time I went back to my office real quick and I just wrote this little chunk of code that showed something that I'm going to show here on the next slide. But it kind of, I mentioned last class we were having issues using, I was trying to show you some of the old string functions. In C, you have to own the memory in order to modify the memory. We were using what are called string literals, where in Java, we can create a string literal. We can say string s is equal to hello, and we own it. We can do whatever we want with it, things like that. But in C, well, the rationale for that is behind the scenes, new memory was being created and all that stuff was happening for us. In a language like C, if we want to have a string, we have to allocate memory for that string. That's what that malloc function does. It allocates new memory. All right, so right here, I'm requesting 1,024 units, let's call it 1,024 bytes of memory. And this is going to create for me what's called a void pointer, a generic memory address. And I'm typecasting that to a char pointer. So effectively, I'm advertising to see that here's a chunk of memory. You can walk through this one char at a time. Treat this like a collection of char-sized blocks, buckets. All right. Then I used a function called string copy to copy my string literal hello into that chunk of memory. And that automatically puts that little \0 thing on it. Then I could show you the string concatenation thing after that, which allows us to extend that. All right. So really, in terms of functionality behind the scenes, no different than what we did in class. I just showed you if we were to own the memory for it. All right. And this is in the slides as well. We'll talk about how big a char is. In an older language like C and C++, chars are 8 bits. 1 byte big. Newer languages like Java, chars are 16 bits because Java supports the Unicode character set, where C and C++ follow the ASCII character set. So the Unicode character set is it's a superset of ASCII. So ASCII has 256 unique characters in it. Unicode has 65,536 unique characters in it. So you need a bigger variable type, 16 bits, to hold that many unique characters. And that's why in Java and C# and Swift, the char primitive type is actually supported by a 16-bit unsigned integer instead of an 8-bit unsigned integer. But other than that, they behave identically. They're both unsigned integers and they both map to some character. You know, the character at bucket 16 in the ASCII set is the same character at bucket 16 of the Unicode set. Just once you get past bucket 255 is when you start getting into things that only exist in the Unicode set. All right, but for C, the size of a char is 8 bits, 1 byte, which means that in our, so here's an example here. If I create a char pointer S, and I allocate some memory, how much memory? 7 times the size of a char, which would be 7 bytes. Okay, in that case, this is going to give me a memory address that I'm going to store inside of this char pointer. This is a little different than what I did here in this, where I just said, look, give me 1,024, give me a kilobyte of memory and let me do whatever I want with it. I built a really, really tiny home on that giant plot of land there. I put hello world onto a plot of land capable of holding 1,024 bytes. But who cares? We got the memory, right? So that's what I did in that particular case, as opposed to in this example, I kind of custom built something for holding exactly 7 bytes. And then I put in there the string hello, which is 5 bytes plus the \0, 6 bytes. So this is 1 byte too big for the what I'm trying to do. So that's in my example here. So when I then set it equal to either like this in a newer language like C++, or using string copy, like I did right here. String copy is just a function that knows how to take a string literal and toss it into a place in memory, a pointer in memory. What it ultimately gives me is something that looks kind of like this. I've just assumed that S holds memory address 100, that malloc, memory allocate. This guy happened to hand us a very convenient in-class example memory address of 100. All right. And so that means bucket 0 is at 100, bucket 1 is at 101, because we're taking single byte size steps through memory, char size steps through memory. Okay. So after I use either string copy, or in C++, I can do this. I can now have, I have HELLO, and then that \0 is at bucket 5, the 6th character in there. And bucket 6 is it's claimed land, claimed memory that I haven't actually put anything on. All right, that makes some sense. But again, we're going to be using C++ style strings in here, but strings are a very good way of kind of exploring this idea of pointers that we're going to be using a lot in here. So this, the last class and a half, let's say, is less about becoming an expert of using old style strings and more about, here's kind of a familiar construct, a string, that we're using to kind of explore this idea of memory. Okay. Talked about that. Most of that's what we talked about. All right. I want to jump into linked data structures here. All right, so in this class, we're going to be talking about data structures. Data structures are structures for holding data. Haha. All right, so effectively, up to this point, we have, you can think of these guys as variable types. Up to this point, we have created, well, used built-in structures for holding data throughout our programming experience. We've used integers and chars and booleans, you know, primitive type variables for holding data. We've also used things like strings for holding data. Last time we talked about a thing that kind of behaves like a Python dictionary, mostly holds name value pairs, called a struct. Okay, so that's something else built into C that is a almost like our evolutionary step right before we get to objects, right? So structs allow us to hold a bunch of name value pairs, but come up short of having functions living inside of them. So we can kind of see maybe the need to have objects. But we can imagine as our programs get more and more complex, as our needs get more advanced, we might need to start writing our own specialized kinds of structures, specialized kinds of variables, probably doing this through a class that allows us to do things in interesting ways. Okay, so in this course, we're going to be looking at linear as well as non-linear data structures. All right, we'll start talking about linear ones today. All right, so under our list of linear data structures, we're going to be looking at linked lists, stacks, and queues. And non-linear, we'll be looking at trees and graphs. All right, several different versions of each of those. We'll look at a couple different versions of trees, binary trees, and look at traversal program algorithms and things like that. All right, so I don't know where the slide set's going next, so I'll just create the slide I want. What's the problem with an array? Did you? I thought you graduated.
December.
Oh, you're in senior sem right now.
Yeah.
Oh, are you gonna fail?
Yeah.
Okay.
Especially if you're grading.
Yep. See you next year. Good programmer, Michael Brocker. So if you have trouble with your homework, he's worth asking for help. All right, so what's the problem with our arrays? Or what's a weakness of arrays? They solve a problem, right? They wouldn't exist if they, just were terrible across the board. But what would we say if you had to point out a weakness with arrays? What might a weakness be? What's the strength? Let's go that route. What makes arrays good? Go ahead. Okay, so we can store lots of stuff, right? So we can have many things instead of stored inside of a single variable. Okay, and so that's one benefit of it. Another benefit is because they're stored in contiguous memory. What does contiguous memory mean? When I say contiguous memory, what does that ultimately mean? That's what the slide showed, right? Where was my slide? This one? This is showing contiguous memory, right? What is contiguous memory? Right next to each other. Okay. And when something is stored in contiguous memory, that means we can go to a base address and then we can jump through memory using pointer math to get us to an exact location in memory where a specific bucket might live, right? So we would say that arrays are fast. They're really fast because we can calculate where in memory bucket 4 of an array is. This guy right here. I don't need to go to bucket 0, then go to bucket 1, then go to bucket 2, then go to bucket 3, then finally arrive at bucket 4. I can say, where's the base address? Add 4 to it. Boom. I'm right here at 104 in this case, because I take char size steps through memory here. So I'm dealing with a char pointer. Chars are 1 byte and big. So 4 times 1 is 4. 100 plus 4 is 104. So I don't have to even go to the beginning of my array. I could just dive directly into memory exactly where I need to be. Make sense? So arrays are fast. All that sounds good. I can store multiple things and they're really fast. But what's wrong with arrays? If you were to point out a weakness of arrays, what is it? Go ahead. Okay, good. So must be stored in contiguous memory. So adding and removing is, let's see, problematic. Not impossible, but problematic. And they are very memory inefficient. And we can see the example of my memory inefficiency from my example on Slack. We would say that my example here in the slides was pretty memory efficient, right? I said, give me 7 bytes. And I mostly filled up those 7 bytes, right? I built a house here and then just had a little tiny back porch type thing. All right. But in my scheme example, I'm sorry, my Slack example, I said, look, give me a kilobyte. Give me 1,024 bytes. And I built a tiny home on it. So I have all of this wasted space. Still fast, because I knew where I had to stop and put that \0 on there, right? So it knew where the string ended, since we're dealing with strings in this particular case. But I still bought a giant plot of land. I reserved that huge contiguous plot of land for what ended up being a very small amount of data. I wasted a lot of space. Okay, so that's one problem. And then, as you pointed out, since it's also required that arrays are stored in contiguous memory, not only did I buy a whole lot of land, it had to be right next to each other, which makes sense in real life, right? If you're building a house, you don't kind of buy one plot of land here, one plot of land across the street, and another plot of land across town and build your house in sections. Sometimes you might buy a plot of land here and maybe across the street you put a barn up or something like that, maybe. But generally speaking, when you're building a house, you build it all right in one place, right? All right, so an inefficiency here is that I needed to have enough memory, not just in existence on my computer, but specifically next to each other in my computer in order to claim, in this case, a kilobyte of memory. So it would be theoretically possible if I had a system with either a very little memory in it, or I already had a whole bunch of stuff taking up memory in my computer, it would be possible for me to have a situation where I technically had a kilobyte of memory in total available throughout all of my memory, but I didn't have a position where a kilobyte of memory in a row was available. That makes some sense? So contiguous memory has the benefit of speed, but has the cost of efficiency. And as he pointed out, making changes to the size of it becomes very destructive. You know, in real life, as long as you have enough extra land, if you want to expand your back patio, you can, right? You just kind of add on. But with an array, if you want to make that array 1 bucket bigger, you have to you have to build a brand new array, copy all your stuff over to it, but make that new array a little bit bigger than the old one. So you effectively duplicate your house on another plot of land that's a little bit bigger. You build your extra patio, and then you destroy your original house. Doesn't make any sense in real life. But once that house is built, it's fast. Okay, arrays are fast. Okay, so we're going to say this is the problem with arrays. We might say, since we have a lot of memory today and computers are very, very fast, maybe this is less of a problem than it used to be. All right, so this kind of goes hand in hand with this idea of, you know, how maybe computer science is changing. I would still argue that what we're going to be talking about in here with linked data structures is very usable, very important, but it might be less required today in terms of the implementation we're going to look at. So when we look at linked lists, and let me show you a linked list first. That'll be let's go this route. So a linked list. If we were building a string hello, something like that. But we're going to say, well, we'll put each of these guys in a place in memory. We'll say that's memory address 100. This is 107, 122, 308, 414. Places in memory that are not necessarily contiguous. They're not sitting right next to each other in memory. Okay. So what ends up happening is we no longer have that advantage of speed. We can't just go to the base address and jump ahead to the plot of land where bucket 4 lives. Okay. So if we want to think about this, this is our theoretical bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. Okay. But we can't just go to this base address and add to get to bucket 1. Say, I'm just going to add 1 to this, which is address 101, and be at bucket 1. is we no longer have this rule where they're contiguous, where they're right next to each other in memory. So that means that with a linked list, each element of our data that we're collecting sits alone and it's linked to the next element in our list. So that means that this first guy stores some piece of information, a pointer to the location of this next guy, who stores a location to, a pointer to the location of the next guy, who stores a pointer to the location of the next guy, who stores a pointer to the location of the next guy. All right, we're going to call each of these guys here, we're going to call them nodes. So this is a node in our linked list. So each of these nodes has a value that lives there. We usually call that a payload. And it has a next node, a pointer to the next node in the linked list. All right, so this guy holds an H, and he also has a next node variable that in this case holds a 107, telling us where in memory the next guy lives. Where in memory the next guy lives, so on and so forth. Okay. So this guy is floating out there somehow. We're going to end up building these. But we need to know where the beginning of this collection of data is. That's usually done through a node pointer called head. And head holds the location of that first node in our linked list. So if we're thinking about designing a class here, we have the node class. A node class is going to keep track of our payload, and it's also going to keep track of a node pointer next node. All right, the two fields that our class is going to hold. Let's go. I already have the. Oh, this is it, right? Let's create a new project here. We'll call this guy CSC300 linked list example. And I'll go ahead and create a new file. And we're going to call this guy node.hpp. We'll create our header file for our node here. All right, so we're going to create a class called node. And we're going to have a private section in here. That we're going to initially create a linked list of, let's just do integers. So instead of hello in this example, things relatively simple. We'll do like a 3, a 7, a 2, a 21, and a 48, something like that. Okay, bunch of numbers. So we're going to have an int payload. That's the value that lives in a particular node. And then we're going to have a node pointer next node. So we're going to know where the next node lives. Then we're going to have our public section. And we're going to create our build our node by passing in a payload. And then we're going to give ourselves getters and setters. Since we put these guys in a private section, these fields are only accessible indirectly through getters and setters. So I want to be able to get the payload. I want to be able to get the next node. And I want to be able to set the next node. All right. I don't want to be able to set my payload. Once I have a value stored, I'm going to leave that value alone for right now. Okay. We might decide we want to change the value that's stored in a particular bucket, but for right now, we're going to just leave it alone. And we're going to say once a payload is set, it's set. But I want to be able to manipulate those pointers because I might be adding stuff to the beginning of a list or adding stuff to the end of a list or adding stuff somewhere in the middle of a list. Okay. And then I'm going to go ahead and also give myself a function called display that allows a node to display itself. All right, so there is our header file for our node. So again, when we look at these header files, we're able to see at a glance what the abilities are of this this particular file. Choose C++ here. So now I'll go ahead and let's create our implementation for Node. So this will be Node CPP. And I'm going to include node.hpp. I wonder, will this work? Can I do that? Oh, Ninja. So let me just give myself my buckets to build this in. All right. So when we build a node, we're going to pass a payload in. That is, we are building one of these guys. So when I build a fresh node, I'm going to say, here's your value, here's your payload, and initially you point nowhere. All right, you point to a value called nil. Is it nil or is it null in C++? I guess we're going to find out. So I'll go ahead and say this payload is equal to the payload that was passed in. And remind me, what does this arrow syntax mean? It's already 11:30. We should be a more talkative group than this. My 8 a.m. language theory classes, like they're already throwing stuff at me. We got we talked about this like the whole last class, right? What's that arrow syntax for? Okay. Value at the address is the star. Okay, so if I have that star syntax that says, give me the value at that address. What's the difference between arrow and dot? That's what we're really talking about here. If I were to say this dot instead of this arrow, the difference between these two things here, saying this dot versus this arrow, those two symbols define what kind of, or they imply to us what kind of value this holds. So if I see a dot here, what kind of value is this? Versus when I see an arrow here, what kind of value is this? A dot says that this variable holds a pointer to a thing, an actual thing, the value. An arrow says that this guy holds a pointer to a pointer, which points to the value. So this says, follow this address to the address it holds, and then resolve that guy to get me this. So this is this particular node. And I'm going to follow that to get to that guy's payload. So this is a pointer to a pointer. Remember last time we said we can replace this with that guy? Those two things mean the same thing. This says, as you pointed out, the star this says, give me the value that lives at that address, then call that dude's payload. As opposed to this syntax says, get the value that lives there and then call his payload. So this is syntactic sugar, which saves us a couple of parentheses and an asterisk. But it tells us that this guy holds an address which points to a thing and needs to be resolved to that thing first. All right, so this payload is equal to payload. And we're going to say this dot next node is equal to, I think it's all caps like that. And I also think that might live inside of standard lib, but we'll listen for the screaming momentarily. Okay, so when we build a brand new node, that's what we're going to do. We'll set that node's payload equal to whatever was passed in. And then we'll default his next node to initially point nowhere, keeping in mind that we have the ability to change where his next node points to. All right. Get payload is just going to return this payload. Get next node is just going to return this dot next node. Set next node is going to say this dot next node is equal to whatever was passed in. And display, for right now, why don't we just have it display the current payload, just for testing purposes. So we'll do this in C++ style. So we'll include IOStream, namespace. So then down here, we can say cout this payload. Actually, before I do that, I just want to see if null lives inside of standard lib. So I won't use endl for the moment. I'll just do the \n. All right, so that is my initial pass at a node. So now inside main, I actually won't need this at this point. I'm going to say include node HPP. And I'll create a node pointer n is equal to a new node, and I'll put a 3 in there, and then I'll say n display. And there's my 3. So that node value, or the null value, sorry, this guy in C++, he doesn't live in a special library. In C, I believe he does. In order to get this guy, he lives in null used to be represented just as 0. That's the default nothingness. All right. Now, if I wanted make sure it'll let me do that first. Yeah, it returns a node pointer, so I can't pull it off. It's fine. All right, so I've created a node now, and this guy's just sitting out in the middle of nowhere. So if I want to steal this guy right here, at this point, my program has there. Something that looks like this. I have a variable named n that visually looks kind of like this. And actually this 0 is not even here because that is the linked list that's going to manage this. At this point, my whole program is made up of just nodes. In fact, it's made up of one node. So I have brought a single node into existence, and this guy lives somewhere. I've just decided it must have gotten the memory address 100. All right. Well, actually, for right now, he points to nothing, but I think the way I had this written was where he actually lives in memory. All right. So this is my node that exists right now. Pretty useless in the big scheme of things. So what I need to do is I need to create another class that manages collections of nodes, kind of like this. And that's going to be something called a linked list. So a linked list is going to be the dude who keeps track of nodes that are linked to each other and allows us to do stuff to that. Make some sense? All right, so we'll go ahead and create our linked list class. Linked list HPP. So we'll have our class linked list. We'll have our private section and our public section. All right, now if you look back at my picture here, I show that this linked list actually has a single field, a field that's going to point to the beginning of the list. If you want to think about this in terms of arrays, it's pointing to the base address of the array, the beginning of the list. All right. What kind of animal is this guy right here? Cat, dog, or node? We heard cat. Is that okay? That guy's a node, right? Okay. So if I want something that points at a node, what kind of variable is that? It's killing me, people. My wife interacts more than this at home when I'm talking to myself. It's going to be a node pointer, right? If that's a node and I want something that points at it, it's a node pointer. So I'm going to have a node pointer called head. Now, in order for me to, I invented node, right? This is my code that I wrote called node. So in order for C++ to be okay with me saying, hey, there's going to be this thing called node pointer here, I'm going to have to include node HPP. Otherwise, C++ is going to say, look, I've never heard of that dude. If you want me to know about him, you have to tell me where you defined him. And I did that inside of my node header file. And then implemented it inside of my node CPP. All right, so I'm going to have the head. Now we're going to have our constructor for linked list. So linked list constructor is going to take in no parameters. And it's going to build an empty linked list. That is a list whose head points nowhere. And I'll go ahead and have a display as well. I'll steal these couple of dudes here. What time are we at? 50 or 55? Okay, good. All right, so we'll go into, we're going to create our linked list.cpp now. And we're going to include linked list HPP, the guy I just wrote. And then I'm going to go ahead and I want to implement these couple of things. Okay. So my constructor for linked list takes in no parameters, and I initialize an empty linked list. And an empty linked list is a list whose head is equal to null. Points nowhere. List is empty. And then for display, if I ask a linked list to display itself, as of right now, the only kind of linked list I know how to create is an empty linked list. I can do a little if statement. If this head is equal to null, then I can do cout empty list. All right, but it's not going to know about cout at this point. So I need to include IOStream. Namespace standard. Now it'll know about that. If I didn't say using namespace standard, I would have to say std like that to call cout. Cout lives in that namespace. It's implemented in IOStream, but it lives in the namespace standard. So I either can include or using namespace standard, so this is presumed, or I could just type it in there like that if I want. All right, so right now we know how to create empty linked lists. Go back to main. We'll go ahead and include linked list HPP. And I'm going to go ahead and get rid of my node because we're not actually going to deal with nodes in main. We're going to deal with linked lists, and linked lists will allow us to behind the scenes generate nodes. Linked list manage nodes. So now I'll create a linked list pointer. LL, it's got to be a new linked list. And then I'll tell LL to display itself, which gives me empty list because there's nothing in it. All right, make some sense? But now we'd like to have lists with stuff in them. So we're going to add a feature to our linked list called add front. And this guy will take in a payload. So when I add front, I'm adding something to the front of my linked list. So whenever I do that, I'm adding it ahead. It becomes the new first element in my linked list. So I'll go ahead and create my node pointer. So inside of here, since now I'm dealing with, actually I did node in my header file. This guy knows about nodes, so I don't need to include it again. So I'm going to create my node pointer. Let's call this guy temp, and he's going to be a new node built with that payload. Whatever that payload was, I have a new node with that payload. So he's just sitting out there nowhere. I now need to make him become the new head of my list without breaking my existing list. So I'm going to say temp set next node equal to whatever the head of this linked list currently points to. So my linked list as of right now points to that node, which might be null, but it's some node up here. Now I just create this brand new node right here. I want my brand new node, this guy, to point at the same dude this guy points to. All right, so now both this linked list head and my node temp are pointing at the same place in memory, either another node or possibly null, doesn't matter. Once I've done that, and only once I've done that, once I have something else pointing here, can I then make head point to my new node. So now temp is the new front of my list that then links to the guy that used to be the front of the list. I've added something to the front. Make some sense? So now if I come back out here to main and I say ll.add front 1, two, 3, 4, and I run this, I just created a linked list with 4 elements in it, but I have no way to show it. If I currently say LL display, it's not going to show anything because my LL display currently only displays if it's the empty list. And I'm advertising that my list is now more than the empty list. Head points to something. We just don't have a way to display that list. So your homework for Tuesday is going to be to expand on this code to get it to get display to work for lists that actually have stuff in them. That make sense? So I think I'm going to be able to share. Yeah, so I'll give you this code link for the starting point for my code. So you should start your project with this, and then you'll submit your link, or if you want to, if you're using a different interpreter or a different compiler, you can give me on GitHub. Give me some link that I can look at your code when you submit it. All right, but your homework is going to be to make this guy work better. Show me more than just the empty list or nothing. He should show me something when it's not the empty list, the contents of the list in some sort of reasonable format. Questions, comments, concerns, bribes? Go ahead.
What day is homework due?
Tuesday, next class, right? Well, what's today? Friday? No, next class Monday. Yeah, homework will always be due the next class. I rarely will give stuff that bridges multiple classes. I might give an assignment that should bridge multiple classes, but I'll still make it do the next class. It's just entertaining for me. All right. This shouldn't be too bad, but this will give you some practice with the pointers and stuff like that until you kind of get your feet under you. All right. Any other questions? All right. I'll see everybody on Monday.